Our next example is asking us to find the volume of the solid that's formed when the region between 2x squared and x cubed is revolved around the x-axis. All right. We can find this, what this looks like, using our graphing calculators. If you do so, we'll see just a very quick sketch. The 2x squared will do this, and x cubed actually comes underneath it. So we kind of have this banana shape happening, and that is being revolved around the x-axis. All right, so this very skinny little region right there is going to get shifted around the x-axis. We want to find the volume of that solid. All right. In order to do that, we know the formula from the previous video, but we need more of the details. All right, we know that we've got pi times the integral from a to b of the outer function, which is r of x, our outer radius squared, minus the inner, or lowercase r, radius squared dx. But which one's the outer and which one's the inner? And where are the bounds? Well, we have to do the same thing that we did back with the area between two curves. In order to find our bounds, we need to set the two functions equal to each other. All right, so I'll change colors real quick. We'll kind of shoot over here on the side. We need 2x squared to be equal to x cubed. And we want to solve, it's ideal to have this equal to 0. So if we subtract 2x squared from both sides, we'll have that difference equal to 0. Now we can factor out a common x squared, leaving us with x minus 2 when we divide out that x squared. And now we can clearly see that the two values of x in which the functions intersect are at x equals 0 and x equals 2. And those will be our bounds. So if I go back over here, I've got pi, and then the integral from 0 to 2, and now I need my outer function squared, my inner function squared. Well, again, if we don't have the graphing calculator available to us, we know from the previous experience that we can find which function of the two is the greater function, the longer radius, by plugging in a value into both functions, and that value of x needs to be between our two bounds. So let's take 1. If we plug 1 in for x here, we get 2. If we plug 1 in for x here, we get 1. This is producing the greater value. It's our outer function. It goes first. So we're going to have 2x squared wrapped in squared minus x cubed wrapped in squared. And our dx is at the end. Now we have the integral, which is going to allow us to find that volume. Once again, the squaring needs to be done first before we can actually come up with our antiderivatives. So if we were to square each of the individual parts here, then we're looking at pi times the integral from 0 to 2. X squared is going to become 4x to the 4th. X cubed is going to become x to the 6th. And we still have our dx. This allows us to take our antiderivative. So we have the pi, which is hanging out front, 4x to the 4th, antiderives to 4x to the 5th over 5, and then x to the 6th, antiderives to x to the 7th over 7, and that's being evaluated from 0 to 2. All right, when we know we plug in 0, we're going to get 0, so really we only need to plug in the 2. When we do so, 2 to the 5th is 32, and we're going to multiply that by 4, which would be 128. So we have 128 over 5. And when we plug in 2 there, 2 to the 7th, just as before, is 128. So 128 fifths minus 128 sevenths. And keep in mind that we still have our pi right here. And we can go further. We need a common denominator of 35. We'd have to multiply this by 7 and that by 5. Feel free to work on that if you'd like to. But ultimately, this answer right here is correct, if not simplified. That works in my book.